one-dimensional potential well and its energy eigenvalues or energy levels. So whenever we have some potential well which is infinite, we write the potential as V of x is equal to 0 when x we can say x is between L and it is greater than 0, and it is equal to infinite for x less than 0 and x greater than L. Okay, so we have this potential and corresponding potential well is given here. So we have three regions. This is, let's say, region 1, this is second region, and this is, let's say, third region. So there are three regions, out of which we will concentrate only in the second region because wave function has solution psi of x is equal to 0 in this region, and in this region also psi of x is equal to 0 because this is infinite potential well and the wave function will not exist in this first and third region. So we will concentrate only in this region. So we will call these wave functions as sine of x and we will try to solve it. So whenever we have to find such solutions, so in that case we will start with the Schrodinger's equation. So that is h psi is equal to E psi, h psi is equal to E psi, where h is the Hamiltonian, psi is the wave function, E is the energy eigenvalue, and psi is again the wave function. So here we have this kinetic energy part and this is potential energy part, and we have energy eigenvalues and sine of x, that is wave function as it is. So in the second region, v of x is equal to 0. So above equation, this part, so this v of x is 0 in that region. So that's why above equation we can write it as minus h cross square upon twice m into this d square sine of x upon dx square is equal to en sine of x. So once we know such equation, we know how to solve the differential equation. So in order to convert it into the known form of the differential equation, we will take this minus h cross square upon twice m on the right hand side, and whole term we will take on the left hand side. So this minus will become plus here. So twice m en upon h cross square into sine of x is equal to 0. So we can assume that this whole part, this 2m upon h cross square into this here 2m en upon h cross square as k square. Okay, so we have assumed that it is equal to k square. So once we have converted it into this, you can say this equation is in the form of known wave functions and differential equation. So we can get the general solution to this equation, and we get the solution as, so we know that general solution as, you can say this sine of x is equal to a sin kx plus b cos kx. So this is general solution to that differential equation. So we have to determine the value of a, k and b. These are the constants which we can determine by using the boundary conditions. So here in this case we have a first boundary condition, which is sine of x is equal to 0 at x is equal to 0, because we have seen that there is a wave function. Okay, so this is, let's say, our potential well where we started with the 0 to L. This is the value of x, and here at this point, as wave function should be continuous, here the value of sine of x is 0. So it will start with the 0, and so in second region it will become, let's say it will be something like this, but wave function will start with the from the 0. Okay, in the both the cases. Okay, so it is 0 in this case, and it is 0 in the first region and in the third region. Okay, and it should be if it is continuous, then wave function in the second region, first region, that is equal to 0, that should be equal to wave function in the second region at this point. That's why this first boundary condition, and similarly we have second boundary condition at this surface. So where wave function in this region is third region is 0, so wave function in the second region should be equal to 0 at this point, so that it will be a continuous wave function. So applying the first boundary condition, what we get is sine of x equal to 0 at x is equal to 0. That's why 0 is equal to a sin k x value is equal to 0. That's why we have substituted the value of x is equal to 0 plus b cos k 0. So this sign 0, this becomes sign 0 into a, that becomes 0, plus b into cos 0. Cos 0 is 1, so b will be equal to 0. Okay, so we can substitute this value in the first general equation, and our equation becomes, wave function becomes sin of x is equal to a sin kx, where we have to determine this value of a by using the we can say, we know the probability of occurrence of the wave function from minus infinity to plus infinity is 1, so we can define it as, let's say, integration from minus infinity to plus infinity, psi star of x into psi of x dx is equal to 1. But wave function from minus infinity to 0, we can split this integral in three parts. So wave function from minus infinity to 0, from 0 to L, and from L to infinity. So because wave function from minus infinity to 0 is 0, and from L to infinity that is also 0, so we will concentrate only in the second region. So that because of this, wave function is 0 in first and third region, so we can write it as wave function integration from 0 to L psi star x into psi of x dx, which is equal to 1. So probability of occurrence of the particle is between from 0 to L is equal to 1. So if this is the case, we can find this integration. So here we have integration from 0 to, let's say, L. A star means, okay, a star sin kx, sorry, a star sin kx a star into sin kx into a into sin kx, okay, into dx, which is equal to 1. So I can write it as, let's say, 0 to L, this is a square mod of a square into sin kx its square, which in dx, which is equal to 1. So we can write it as mod of a its square into integration of sine square from 0 to L, that is well-known quantity, that is, you can say, L by 2, okay, which is equal to 1. So a is equal to root 2 by L, so that is the value of a, and this process is called as normalization. Okay, so normalization. Okay, so by using normalization process, we have calculated the value of a, and a is called as normalization constant of this wave function. So once we have this normalization constant, final wave function becomes sin of x is equal to root 2 by L into sin kx. So okay, so now we have to determine the value of k. Okay, we will see determine it. Now we have started with sin of x is equal to a sin kx, applying second boundary conditions. Second boundary condition gives us, okay, what is that second boundary condition? Sin at L is equal to 0, at x is equal to L. That's why sin of L is equal to 0. So this 0, which is equal to a sin k into L, value of x is equal to L. That's why I have substituted value x is equal to L. So we have this equation. So if the product of sin kl into a is 0, that means either a is 0 or sin kl is equal to 0. If a is equal to 0, that means wave function in the second region is 0, and in that case there is no particle in the infinite potential well. So that okay, so there is no meaning in solving such problem. So we will assume that there is a particle inside the potential well. That's why this a is not equal to 0. So sin kl should be equal to 0. If sin kl is equal to 0, that means kl should be equal to n pi, where n is equal to 1, 2, 3, like this way up to infinity. Again here, if we put the value of n is equal to 0, that becomes, if I put the value n is equal to 0, in that case, that again becomes a trivial solution. That means the particle don't exist in that potential well. So what we have taken value of n, we start from 1 2 3 like this way up to infinity. So n is equal to 1 gives the ground state energy state. So here n is equal to n pi upon L. So I have substituted it here in this equation. So finally I can write the wave function as root 2 upon L into sine n pi x upon L. So this is wave function. So depending on the value of you can say n, we can write the wave function in different forms. So let's say psi 1 of x, that is root 2 by L into sine pi x upon L. So this is ground state wave function. Okay, so like this way we have calculated the ground state wave function for this video. Thank you for your watching.